Okay, I've had time. Please bear with me if I'm still making video angle mistakes because I'm not a professional cameraman. But yes, this will now be an IBHL AI Mathematics Applications Interpretation Oxford Course Companion by Doring and Economopoulos et al. And we're going to do a bunch of two differential calculus sort of problems today, and we're going to use the TINSpire. So first one is going to be, I'm going to give it an abstract, but fortunately you have numbers. So I'll give quickly the way you can cheese it. You have the calculator, but you have to show the work, then show you the steps you need to put down. So you have a circle here, define the center there. Like, it splits out this particular sector here. However, what we want to find is an area of the segment, which is a stupid name, in my opinion, but it's basically the area of this little thing over there. And what's the typical way to go and find the area of a stupid, like, complicated looking shape? You take the difference of two more simpler shapes or stuff. In this case, I'm getting ahead of myself. First, let me go and like spell out all the given stuff. So you have points A and B. This is point A. This is point B. This is point A. This is point B. They subtend an angle theta, and this radius is 5 centimeters. Now you are given then that so the angle AOB, and O being the origin, is increasing at a rate, I don't know whether it's clockwise or counterclockwise, who cares? But the rate of the angle increasing, angle AOB dt, is around 0.2 radians per second. And I guess I could call this for our intents purposes d theta dt as well. Now, on which the area for our minor segment is increasing. So basically find dA dt of segment. When theta equals 1. Okay, so first things first, we need to find the area of this segment. Now we get to what I was rambling about. You want to find an area of a stupid convoluted shape, you gotta take the difference between as many simpler shapes as you want. In this case, particularly 2. You want to take the area of a sector and then subtract it by the area of this triangle here, inscribed inside the circle. So the area of the segment equals area of sector of a circle minus area triangle. This is going to get gnarly. Okay, sector of a circle, that's basically a fraction of the area of a circle. So, assuming we're working in like pi radians, radian land, that's like theta over 2 pi for a fraction of pi r squared, area of a circle. And then this is being minus by the area of this triangle. Now, it's not a right angle triangle. We can't form a perpendicular length. So in general, we have to unfortunately go and appeal to using some trigonometry, which is mainly that this is minus 1/2 times the 2 side lengths here times the sine of the angle in between them, which in this case would be r squared and then sine theta. You can show some work. The pi cancels here, so you get 1/2 theta's r squared, which necessarily has to work in radians for this to work. I just derived why it works. Minus 1/2 r squared sine of theta. And if you want to tidy this up here, you can go and put this as 1/2 r squared times theta minus sine theta. Okay, yeah, that's good. Okay, and that's a function of, it's basically the area of the segment as a function, not just of, well, the r is constant. The r is constant for this particular case, so it's really a function of theta, but since we have r, you could technically vary the r if you want. But for simplicity, let's keep r constant. So then a of theta equals 1/2 r squared theta minus sine of theta. Yeah, I hopefully think we're going to assume, let me just check, we're only assuming that like the angle is changing. Yes, it's a circle with radius 5 centimeters, and that circle is not changing. I'm going to assume that that circle just remains constant in time. Yeah, okay. So if you have to go and like do the derivative of this thing, okay, let me go and like take a word with the TINSpire now. So first you have to go and define that in your calculator. However, unfortunately for the TINSpire, you do have to go and put it in terms of two variables here, because you have those two parameters. Now let me go and get this stupid, I hate this calculator, absolutely love it, and then tell you what to do. So let's see here, then we go to menu. You have to go to actions to go and define your new function. Let me just call it A, because unfortunately I can't make it capital. The TINSpire is stupidly case insensitive, so you're just gonna have to deal with that. And then you go and put in your inputs. It'll be r, comma, theta. To go theta, you have to click the blue button here, and then go to this letter here to get the theta there. And then you just plug in that formula you have there. Let me not do enter, otherwise I'm going to do something stupid. Okay, yep, and then we can just express it in that form. So 1 times 2, you know what, just so that there's no mistake, let me do 0.5 times r squared times, oh Lord, give me a second, this is theta minus, this is painful, this is absolutely painful, I'm not good at this at all, minus sine of theta. So control the blue button, you need the Greek letters here, and then this. Okay, that's done. Enter, done. And let's see, I could then like do a derivative of that with respect to one variable. So I go to, because like all we're given is like, we want to find a dA dt, right? And we just are given that like theta is 1 and d theta dt is 0.2 radians per second. Oh, hang on, but by, okay, you know, I actually have a feeling we need to go and like put some stuff in. Okay, you can't escape. You have to do some actual work here, I believe. So actually first let's go and compute the derivative of this right now with respect to time. So that means this theta is a function of time as well. It's just a nasty composite function. A of theta of t, 1/2 r squared. R is constant, thank God for that. Theta of t minus sine theta of t. And now we do the usual stupid stuff. So like dA dt is basically going to dA dt in Leibniz notation is going to be dA d theta. You do that composition first times d theta dt. have to go and like do this like separately. So let's see, theta t, that's just going to be d theta dt. So you have 1/2 r squared d theta dt. And then you have minus sine theta of t. So then that's going to be minus cosine. Minus sine. You do the minus sign over here and then you rotate it again, it's going to bring us to minus cosine theta by rotation, mechanical rotation. So that's minus cosine theta of t. And then you multiply by the angle in that again, so you get a d theta dt. This cancels out. Okay, this is not that bad. I don't see like why you need a calculator for this. So, okay, this is it in general. And then if you want dA dt when theta equals what? Yeah, something is right. Something is not wrong. Where do I have the theta not appearing? Oh, okay, theta is 1. When theta equals 1. Okay, at an uncertain amount of time. Let me just check that I didn't mess this up again. Let me just check. I know it. I forgot to distribute the 1/2 r squared. So this is again 1/2 minus 1/2 r squared. Cosine theta of t, d theta t, d theta dt. That's painful. Okay. I just like make it easier on our lives. 1/2 r squared d theta dt. I can just factor all that stuff out to get 1 minus cosine of theta of t. So then doing this over here, we want dA dt given d theta dt, given theta equals 1 and d theta dt equals 0.2 radians. So then I have to go to here, and then 1/2 r squared. Where is the r? What's my r? Oh, it's 5. 5 squared times the d theta dt, 0.2. And then I do 1 minus the cosine of that angle, which is just cosine of 1. That's going to be nasty. Is that 1 radian? Let me check again if that's 1 radian. They didn't give units, but everything else is in radians, so I'm going to assume that charitably it's like nice, that this is like 1 radian. Okay, 1 radian. Yeah, they gave this as radian per second. Okay. So then you just like, you can compute that like manually with the calculator. I'm working with the TINSpire stuff now. One thing I need to do is like I previously put the calculator into, as you can see here, it's in, oh my god, do not do this to me. It's in degree mode right now, right? But we're working in radians, so I need to switch. In order to do that, you go to the home menu or the menu button. Yeah, you go to home, which is this house button. On the document side, you scroll down to, wait, isn't it? This is odd. I was able to scroll this and I was able to give me the thing. Hang on, bear with me. This is stupid embarrassing. I said, okay, go to the menu. Sorry, there, so it's dock. I'm sorry, it's not the home button, it's the dock button. Then go to settings and status, which is 7 here. And I believe it was document settings when I went to, here we go. And there you can go and change the mode Oh dear, did I not? Again, I'm very terrible at camera work. This angle here, I can change from degree over to... Oh, what's this gradient thing? Whatever, who cares? Leave it for the geometers to worry about. This is radian mode. I said okay. I said okay. You stupid piece of... Okay, done. Done. So this is good now. We're okay. We're all okay. And now it's like RAD right up over there, as we wanted. Now I derived that formula or stuff, but you can't do it and you want to like hack with the calculator. You could do like numerical derivatives, so then go to calculus menu, calculus 4, numerical derivative at a point. No, that's not what you gave me. 1. There we go, okay. Thought I clicked something a bit off. Okay, and the variable is in terms of theta, because we're leaving the r constant. So let's just go to control theta value. Oh my god. Theta equals 1. However, unfortunately, it also depends on the 0.2 radians per second. You're not giving that input, so I don't know if you're able to do that. But just because this is just fiddling around with the calculator, we'll try anyhow. Oh wait, no, sorry, let me get back. This is 1. And then to go and recall that function very quickly, just go to variable, store. You see you have a here, click enter. And then do it with like r and theta. You gotta like define the arguments r and theta. Maybe you can get away with it, but I'm not taking any chances. So then r, comma, and then... Why is the r highlighted? This better not screw me over. Variable is not defined, no values assigned to variable, use one of the following commands. God damn it. Oh. Oh wait, I'm a moron. I'm differentiating with respect to the angle theta. It should be with time. That's stupid annoying. That's stupid annoying is... no, that's gonna take too long, because then I have to do like a theta of t in there. Oh my god, this is not happening to me. This is not happening to me. Okay. If this takes too long, I'm gonna have to like go and like kill the thing. This is so stupid. Okay, now how did it say for me to delete again? Alright, sorry, I'm just gonna have to move on. Okay, abysmal failure on my part. I'm still don't have enough time to do this, but I need to get like content out. It's needed. So it should be in terms of t. You should have in terms of t in there. Probably screwed in that matter. Sorry, I'm just gonna have to do this like the analytical method, which is like purely with like formula. So then just go and like put in those numbers in there. That's 25 over 2. That's 2 over 10. And that's 1 minus cosine of 1. I just know lucky that it's just 2.5 times 1 minus cosine of 1. Like I said, I'm not a very good cameraman. 2.5 times 1 minus cosine of 1. Enter here. And there we have it. The error is changing at like this particular rate. So it's 1.15 if you round it up to like 3 significant figures. So 1.15. 1.15 centimeters squared per second to get the dimensions right. And is that all they ask of us? Yep, that's all they ask of us. Otherwise, in general, it would be applied to, you're basically using this formula for the dAdt in general. And yeah, I screwed up because I didn't insert in like I didn't insert free variables. It should have r, theta, and t when you define this stuff together. Although unfortunately, the complicated thing is, like, I need to give this d theta dt, and I don't know the TINSpire can do that. I don't know if you can, like, manually plug in, like, your assigned derivative for this. You can give the r, you can give the theta, and the r is constant, but, like, I don't think you can give it, like, the d theta dt. It doesn't give you like the formula automatically. So yeah, it's just gonna have to be like this for now. Okay, and now we go to the next one, which is brutal. It's extremely brutal because it's hell, and I have, for the AI audience, if you don't know, if you can't do this like very quickly, I don't blame you, because it's a show question. It's a show that a differential, the particular functions fulfills a second order differential equation. And I'm like, why do you, fine. I mean, you kind of like need to do this stuff. You can't do everything, like purely a calculator. That's why this course has been like devalued, although I think they do a couple of very important stuff. So I'm not gonna even get the real life situation. You just have a displacement function, x of t, for t is greater than or equal to 0. And we define our function as e to the minus 2t times cosine of square root of the 12 only, not the t. Please do not do like the square root of the t. If you do that, then you make your life extremely harder than it needed to be. So only the square root of 12 is a fact. You're never going to deal with like cosine of like a nested square root function. It's just horrendous. Okay, and then you need to show this satisfies the following differential equation here, which is that d squared x dt squared plus 4 dx dt plus 16x equals 0. A whole bunch of stuff just to show that the differential equation gives you 0 in the end. So this is going to be extremely painful. So I have this stuff, like the first derivative is fine, but the second derivative, it's going to be a bit of pain to get the stuff to work. So, okay, how do we do this? We want to go and identify like the component product functions or factored functions. If you want to show it step by step, unless you're really good enough with doing the shortcuts, then go ahead and do what you do. But like the product rule again is like you leave one function constant, you differentiate the other guy, and then you add it with Well, if this is kept constant, then now you keep this constant, and then you differentiate this other person. So all I'm just going to do is like break up. I'm not going to write the product rule, just so you know it. So then you have u of t equals e to the negative 2t, and then you have v of t equals cosine of, and the square root of 12 is just a constant. We can just leave it like there, square root of 12. Otherwise, if this were a function, you would have to go and raise that to t to the 1/2 power. But like I said, it's only a square root of 12. There is no, the t is not being raised to the square root. Okay. du dt. When you differentiate an exponential function, you get an exact copy of this function back, with, in addition to the chain rule of the stuff nested in there. So you get e to the minus 2t times negative 2. And then when you do dv dt, that's cosine, rotate down, that's minus sine, square root of 12t. But you get a square root of 12 from the square root of 12t by the chain rule, so that's a square root of 12 as well. And now, for a nice visual analog, you just do like a cross diagonal of these things together, and that gives you the first derivative of position with respect to time, which is the velocity function as well. So that's, minus square root of 12 sine square root of 12t e to the minus 2t. And then it's minus this again. Oh no, please don't tell me I did a... Oh wait, sorry, not minus, plus. So it's minus this. Good. I thought I made a stupid mistake for a second there. Minus 2, let's keep everything consistent here. Minus 2 cosine square root of 12t e to the minus 2t. Okay. Okay, and now, boy, it's up to you, but like, when you do the second derivative, you're going to have to use the product rule twice. One for this guy, and one for this. And there's just no helping it, I'm afraid. You could do, this is what I did, but ultimately you can do it like 1 by 1 if you want, works for you. So, I don't know if this is going to save time, but dx dt, we can factor out e to the negative 2t from there. And heck, actually square root of 12, that's 4 times 3, so that's 2 root 3. That's 2 root 3. Okay, I'm just going to factor out a 2 from there. I get a minus 2 e to the negative 2t root 3 sine of square root of 12t minus, no, plus cosine square root of 12t. And be very careful, the square root doesn't go under the t. If you know that, then you screwed up. And now you just have to go and do the product of these individual guys, which is going to be very nightmarish, so I'm going to have to go and like erase this now. But that's your function, that's the first derivative function, so then, please don't, okay, erasing now. I am just afraid I'm erasing stuff that I'll need later. Excuse me. Oh, actually I should have left it as square root of 12 something. Okay, you know what, never mind. Let me go and rewrite it. No, actually I looked at my calculations. keeping it at the square root of 12 is actually more advised. So this is minus e to the minus 2t. It's all the same. I'm just keeping the square root of 12 intact. Square root of 12 sine of square root of 12t plus 2 cosine of square root of 12t. Okay. And now you have to break this up again. And let me see how. Okay, good. I'm biasing with the. Okay, so this is split up into a factor. We'll define a of t equals minus e to the minus 2t. And then b of t equals this garbage. Oh yeah, product pitch here or something like that, just to make everyone's lives easier or stuff. If you are doing your IA, unfortunately this will not save you like during the exam if you're stuck with whatever calculator model you have. But if you're doing the IA and you need to go and like find like these derivative formulas or integral formulas, quickly, don't waste your time like deriving them like by hand analytically. Like use Wolfram Alpha. Wolfram Alpha is a free computational engine as long as you only get the exact final answer. But if you want them to show the steps, you have to pay a subscription fee, and then, well, I can't go on the profanity train. I'm sorry, this is PG rated. DADT. So the negative 2, so that's 2e to the minus 2t. And then dv dt. That just happens to be square root of 12, square root of 12. That comes up at the chain rule, and then you get cosine of this, square root of 12t plus. Well, actually, it's actually do easier by hand. This will look more intimidating when I was doing it on a computer. And then this is minus 2 square root of 12 sine square root of 12t. Oh god, and now I cross this over. And now that's going to look painful. That's going to look painful. I'm sorry, why am I doing this? This should be the acceleration function. d squared x by dt squared. And the derivative of this garbage is this here, cross these things over here. You just trust me that you somehow get minus e to the minus 2t 12 cosine square root of 12t. Again, the t should not be underneath the bracket there. Minus 2 square root of 12 sine of square root of 12t. I hate my life. And then this is plus 2e to the minus 2t somewhere here. Probably this guy. And then, okay, so exact copy. It's exact copy of this. Like square root of 12 sine of square root of 12t plus 2 cosine square root of 12t. Now you're gonna expand and foil all that nightmare stuff. Yeah, I won't do it. I'll sacrifice myself. Okay, this goes by now. I have to go and margin it a bit more to the left. Do I have the... Okay, let me just put this so I can like use a bit of room. So then dx dt minus e to the minus 2t. my life, this is square root of 12, sine of square root of 12 t plus 2 cosine of square root of 12 t. Okay, this will be when we put the final answer of the nice use formula we want for the acceleration. But for this here, okay, step by step. So first thing I do is I go and distribute, which this goes into here and here and here. So it's just going to look ugly, but all I'm doing is for the first step, actually I'm going to outline here. Like, so step 1, oh, you're not reading the right step. So one is distribute. That's what I really do for one line. Second line that I do is I go and factor. What do I factor? I factor the trig terms. But you can factor the exponential terms if you want. And then I add the remaining exponential terms. Okay, so that's just all that's going to be, which is basically this garbage. I think that the word might as well just copy it down. Pain. Minus 12e minus 2t cosine square root of 12t plus 2 square root of 12 e to the minus 2t sine of square root of 12t plus 2 square root of 12 e to the minus t sine of square root of 12t plus 4 e to the minus 2t cosine of square root of 12t. Now I go and factor this out. I got a cosine of square root of 12t minus 12 e to the minus 2t plus 4e to the minus 2t plus sine square root of 12t, and that's. Oh, did I just like add those together? Okay, yeah, I did. Slopping me. I'll just go 2 square root of 2 plus 2 square root. 2 square root of 12 plus 2 square root of 12, which is just double that. And then everything is like an e to the minus 2t. Okay, I factor out some stuff extra, but you can factor out the e minus 2t from there as well. And then that's easy, you just factor out the e minus 2t from this in general. You get cosine of square root of 12t. That's minus 12 plus 4. I won't bother to highlight this. Minus 12 plus 4. And then 2 root 12 and 2 root 12. So that's minus 6. Oh, I'm sorry, that's a plus 4. So that's a minus 8. Right? I should have a minus 8 for this. Minus 8. And plus sine square root of 12t times 4 square root of 12. And then you can simplify that. So then you can get it e to the minus 2t is, yeah, I'll just put 4 root 12 sine of root 12t minus 8 cosine square root of 12t. I don't know if you need to show. No, it's an analytic problem. I don't know. I'm not the one who designed this. This was the show IB AI textbook. So it just needs to be. Let's see. Yeah, if you want, I could do like 4, 2. I can simplify this radical. Square root of 12 is 4 times 3, 2 root 3, 8 root 3. E to the minus 2t, 8 root 3. Sine of square root of 12t minus 8 cosine of square root of 12t. And then I can just factor out that 8 out from there. Whoop-de-doo. Whoop-de-doo indeed. To get 8e to the minus 2t square root of 3 sine of square root of 12t minus cosine square root of 12t. And that's the final. So we got 8e to the minus 2t square root of 3 sine of square root of 12t minus cosine square root of 12t. And then you have to go and put everything into here. This is going to be annoying. So we get this. Actually, how do you go and like distribute everything in this case here? Because then we're going to have to like go and like add stuff together. So then, yeah, let me actually distribute this stuff here. It'll be easier this way. This is going to give 8e to the minus 2t 8 square root of 3, 8 square root of 3, e to the minus 2t, sine of square root of 12t. I can't turn on the board. I need to focus on this right now. Minus 8e to the minus 2t, cosine square root of 12t. Like that, and then this becomes square root of 12 e to the minus 2t. No, sorry, minus square root of 12 e to the minus 2t sine of square root of 12t. Oh my lord. Minus 2 e to minus 2t cosine, so cosine stuff, yeah. Square root of 12 over t. Okay, now we go and like bring in and like expand these like all together. I don't even know how long I'm doing on this. Well, it's better than, is that 10 minutes? Whatever. So then d squared x dt squared plus 4dx dt plus 16x. Here we go again. Plus 4 times this utter nonsense. And then plus 16 times this nonsense, e to the minus 2t cosine of square root of 12t. Okay, I hope you're happy with that. I'm going to just erase this now, because I need room to go and write the final cancellations. And then we just do a bunch of factoring of like e to the negative 2t, and then sine the square root of 12t and cosine the square root of 12t. So the e to the negative 3t, that's going to be a universally factorable thing, thankfully for us, because every single term has them. And then we're going to have like sine square root of 12t being multiplied by some stuff. In the meantime, we're going to have plus, it's going to be weighted by cosine of square root of 12t times, I'm sorry, let me go and, it's a bit bad bias margining. I'm going to do plus cosine of square root of 12t times stuff here. And then we're going to just fill in the weights or whatever, and then this should cancel to 0, this should cancel to 0, so the whole damn thing becomes 0 in the end. Okay, let's see what we got. Pain. Eight root free. Eight root free. Minus 4 root 12. Okay, that's it. That's it for this one. And then this one would be cosine stuff here, so that's minus 8. And our cosine here, oh, 4 times 2, so minus 8 again. And then plus 16, there we go. That's good. That's good. And then just to save time, because like this is going to be minus 16 plus 16, that's the 0 pair, that cancels out this thing. Delicious. And then this stuff, I guess, yeah, just magically cancels out. You can plug into a calculator, but 8 root 3 minus 4 root 12. Root 12 root 4 times 3, so is 2 root 3. So then this is 8 root 3 minus 4 times 2 root 3, which is 8 root 3 minus 8 root 3. You are canceled, buddy. You are canceled. Absolutely canceled. So all this crap becomes 0. Okay. All that for a drops worth of blood. Sorry, that's a bit too edgy. For a drops worth of water. 2 drops of water. And that's just one part. That's just one part of the question. So with that being done, we go to the other parts of the question here, which is what? Sketch the graph of x against t for 0 between inclusive time from 0 less than or equal to t less than or equal to 2. Okay, yeah, this, yeah, all calculator here. Just go all calculator here, go to, sorry, excuse me for a second. Okay, brief word on TINSpire, and this is a thing that I hate about this as well. If you store something, like define stuff, into the main interface system here, you cannot call it and then put it into the graph. They have to be done separately, which I find to be extremely stupid if you're gonna like make it, anyhow, of negativity. So go to graph here. And unfortunately, everything is in terms of x, so although it's a function of time, I'm going to write everything in terms of x's. So then this is e to the minus 2 x, where is the x? X is here. Times cosine times cosine of square root of 12 x. Make sure the square root does not contain the x. It has to be separate from it. Otherwise, you're making your life much more harder than it needs to be. All right, like this. Then click enter. Click enter then as a result. Okay, we don't care about the stuff in the negative. We only care about this particular 0 to 2. So then you just have to go to the window zoom, and then window settings. Let this be 0, let this be 2. Let's see how we do with these predetermined Ymax and Ymins. It's a little bit exaggerated. You don't really see a dip over there, which I've seen from previous things. Let me go and like change the window. This will be -1. Yeah, do the negative here, not there. That's a subtraction sign, completely different. -1, and then this is +1. There we go, that's better. We can get like a bit of the curve here. So then the next question that they asked us after this is done, and that was just like part A. Sketch the graph. So then that's A. Sketch graph of t versus x of t for 0 less than or equal to t less than or equal to 2. And yeah, just for that interval of interest, we're just going to be purely biased in like the right-hand quadrant. Actually, no, the first and the fourth quadrant, actually. There. That's t, that's x of t. That's done. Second part is done now. Okay, now find the time when the bearing first comes. So yeah, just to let you know, this is like a small metal bearing on spring oscillating inside a cone of liquid. But find the time. Okay, so now we have to go. Okay, let me just draw the picture. You have some liquid, yay, and you have a spring, and it's got a metal ball, and it's bouncing up and forth inside there. That's just it, it's damp motion. Find the time when the bearing comes to rest. That's A. Find the time when the bearing first comes to instantaneous rest. And its distance from the equilibrium position. And you can rightfully claim that my cursive is like illegible. I'm just doing this to write it quickly. Okay, so then this part. This basically happens when the velocity is 0, when you have a turning point. So when dx dt equals 0. So in this case, not just because we're in AI, because like we don't want to like just bother like saying this stuff analytically. Who cares about analytical solutions? Let's just do numbers. Go to your TID 4 now. And now go and do analyze graph under 6. Then find the minimum, because that's what it is over here. And then just go and define... Oh. Son of a... What is going on? Oh, it's dragging the thing. We apologize for technical difficulties. Well, somehow that just miraculously worked. Yeah, I just like this minimum and I scrolled the entire thing. That was very lucky. Was that the same point that I got? I need to check. Yep, it is. It is. And they're just interested in, well, they're interested in the time and the distance from its equilibrium position. So the time first comes to rest. So this minimum point, just from what we found here, let me see if I can... Okay, text label here. Thank you. Sorry about that. Ignore this point here. Ignore this point. This can be deleted. That's the maximum, probably, some local maximum. But this local minimum is 0.756 and negative 0.191. So then this here (0.756) negative 0.191. Okay, so they want the time. The time is basically the x-coordinate here. So then t equals 0.756 seconds. However, if you want the distance from the equilibrium position, be careful, that is a scalar. That unfortunately does not take any sign, so you need to take the absolute value of this y-coordinate that we found here. And then that'll be in meters. Or is it like centimeters? I'm going to assume like this is in order of magnitude of centimeters. Ah, they don't give it. Fine, okay, I'm going to assume centimeters or like or meters, etc. So this is plus 0.191 centimeters. That's this done. Thank goodness. And let me just go and put this here. dxt equals 0. And particularly since they give us, call it like a minimum as well. Oh no. Do not tell me there are two solutions for this. Find a time when the bearing first comes to... Okay, the first time. Okay, it's the first time. Okay, good. I didn't have to worry about the local maximum. Oh my god, because if they want all the times, then unfortunately you would need to have this particular point as well, assuming this is a maximum. But they just want the first, so we're good. Okay, find the maximum speed of the particle during its first second of motion and its distance from its equilibrium position at this time. So then yeah, that's when t equals 0.756 seconds. And this is, yeah, distance plus 0.19. So I had time to go and review the previous video footage for part C and D of that second order differential equation problem, and I realized that I got part C and D of the question completely wrong. Actually, now I'm not so sure, but I'm gonna do like a more complicated version just in case they were asked you this question. Plus, I realized that like when I showed my graphing calculator, it was not center to the. Okay, so it's like back here. There, that's where the camera is. Okay, I need to remember that's to the left end of my computer. So here, this is what your function x of t equals e to the minus 2t cosine the square root of 12 times t should look like. And remember, as I said, the t should not be underneath a square root. It's only the coefficient square root of 12 that is being weighted that way. So when you look at the function, it looks like this, and I found like the minimum over here. I found my best estimate of a point that's basically t equals 1, because then I have to go and then find the numerical derivative at this particular point. I did it, and I got the result of 0.401 centimeters per second, which is, as you can see, is in green. As represented as a tangent line on that graph there. I don't know yet how to draw a tangent line on here. But essentially after that, I think stuff is easy because what they want is the distance from the equilibrium position. This is where you're lucking out. So ultimately, distance is a scalar quantity, so it has to be positive. So this is a time where it comes to instantaneous rest. So t is approximately t rest first time is 0.756 seconds. And if you wanted other times where it wanted to rest, then you would technically need to identify all the critical points on here, which could not only just be a minima here, but it could be a maxima, one of which is over here as well. Or I don't know, you might even have like a horizontal, no, there's no horizontal inflection point here. But, well, this could be a horizontal inflection point as well. But the types of critical points you'll get are either horizontal inflection points, or the first derivative of 0 is horizontal inflection points, local maxima, local global, it doesn't matter. Maxima, minima, and or horizontal inflection points. So you might have to do this if they ask you for a second time, or times plural. But since we just care about the first time, this suffices for our answer here. Now distance, relative to the equilibrium position, what I'm going to draw it is here, is just, you just do negative 0.191 and do the absolute value of it. So then, absolute value of x of 0.756 is just the absolute value of negative 0.191, which just becomes plus 0.191 centimeters. However, unfortunately, if you are doing this, and this is only if, I'm adding an overcomplication here, if they ask for the total distance traveled since t equals 0, that you need to break up this displacement function piecewise and do absolute values with respect to where this function crosses across the horizontal axis, which would be the zeros of the function. So, in short, you need to pay attention to the key points would be the endpoints of your graph in question. So 1 is 0, 1. Now I'm going to go and find what, give me a sec here. let me find what x of 2 is. No, delete that, delete that. Why is it not letting me change the graph trace here? I'm going to... Oh, okay, here we are. Oh, okay. So for the trace on the TI-84, you just have to do trace, and then it gives you the entire interval, and then you just press like the left and the right button along this blue exclamation point to see what values you get. So yeah, roughly around there, negative 0.15 is the point. But as I go along here, if I go to the very end of the interval, this should be... Oh, whoops, and I... Looks like it went over there, so I'm just going to stop at the 1.98. So then this is roughly around 0.016. Okay, and I trace here for the maxima. Yep, that seems to be the biggest value. It doesn't, it reaches 0.031, and then it doesn't increase from there afterwards. So I'm gonna go to menu, and then I will analyze graph 6, then do a maximum. Then I basically put the lower bound here, and then elongate it there to get the right upper bound. And indeed, it gives it to me at 1.66, 0.031. So this is 1.66, 0.031. And I have to care about like these two zeros as well. So this is a local minimum. This is a local max. Possibly could be a horizontal inflection point. I'll abbreviate it as HIP. This is the left endpoint. This is the first zero. This is the second zero. And this is the right endpoint for the domain that we're looking at here. Okay, let's go and find out what the zeros are here. So then essentially here we go to menu, analyze graph. I go to 0, 1, and I can trace it by here, or really I prefer just like moving to the left. Wait, no, I need to undo that. So the lower bound is here, and then I stretch out to there, get the upper bound. Yeah, now let me... I hate this click and drag thing with the text here. Oh great, no, now it's highlighting both. I hate technology. There we go, it's 0.45 free. It's 0.45 free, and then 0. And then for the very last point on here, I go to analyze graph, 0, lower bound here, then upper bound there. And that gives me, it's a bit like funky, but it's like 1.36, comma 0. So this is 1.36, comma 0. Now, I think if it's distance to the equilibrium position, then this 0.191 centimeters is fine. But this, if they want total distance, I need to have like travel. I need this distance here as well as this distance over here. And then add those up together piecewise. So then if that were the case, I would need to go and find, this would be the same as absolute value of, yeah, this would basically be absolute value of x of 0.453 minus absolute value of x of 0. Plus the absolute value of x of 0.756 minus x of 0.453. And we have part of that already. So in this part over here is this, the 0.191. But then it's being added with the length from like here to there, which is essentially just going to be 1. So then the total distance traveled would be 1.191 centimeters. Okay. Now, if you want the maximum speed, okay, so we found that. That was like absolute value of dx dt, and here we don't have to worry about the sign because it's a positive slope already. So then just taking the value as it is suffices, which is 0.401 centimeters per second. And if you just want the distance from the equilibrium position during this time, all you just need is the y-coordinate of that thing, and then take the absolute value of it. So then the distance from the equilibrium position at this time simply just becomes absolute value of x of 0.756. Oh wait, sorry, from 1. From f1. Oh, at the first second of motion. I'm sorry, I forgot, I made a mistake there. So, it's too much stuff. So the 0.1 corresponds to negative 0.312. So then this point over here is 1, negative 0.132. So then I basically need to do that, absolute value of that, essentially. Absolute value of x of 1 equals positive 0.132 centimeters in this case. However, very similar to this, and I've run out of room to write on here, so now I need to, oh no, it's all blocked out, isn't it? There, I hope you can see it from here. I don't think that's a good enough angle. Okay, there, that will do. Now, unfortunately, I've run out of room here, so I will need to continue in writing like part B over at this point here. This is going to be nasty. I already parked up the room, so like part D. this is getting bad. This is sucking. So suppose they were nasty and they asked for the total distance, which is what I initially thought it was. Just so that you know, these are correct. These are correct. So this, where is it? This time is correct, and I believe, unless I made a mistake, this distance from the equilibrium position is correct as well. Same with this maximum speed here at t equals 1, and this distance from the equilibrium position. This is correct as well. But if they were nasty and they asked for total distance, once again, you have to go and break it up into absolute values. So that's even nastier, because like, you're traveling down here, and then you're moving back up by a little bit. So just to make it a bit easier, you travel all the way down here, and then you go up a little bit until you reach this point over there as well. So yeah, it's here, then there, and then back over there. And then you need to do that. So that's 3 intervals that you need to pay attention to, unfortunately. So if you want the total distance, that will equal, and I'm just going to write in like this right now. So this is going to be absolute value of x of 0.453 minus x of 0, if you do it formally, plus the absolute value of x of 0.756 minus x of 0.453, then plus the absolute value of x of 1 minus the absolute value of x of 0.756. Then have those together, so that's going to be 1. It's going to build up, so it's going to be 1 plus the 0.91 here. And then if that coordinate is 0.132, but that's relative to 0 though, unfortunately, so you need the opposite of that. So you just do, you know what? We're just going to have to do a nasty difference here. This is going to be negative 0.191 minus 0.132, and you do the absolute value of that. Wait, or did I have it wrong? No, I want the opposite direction. No, this is good. 0.132, and then the absolute value of that. So just all those numbers add together, so that's 1.191, and plus this nasty mess. Which, dear God, now I'm going to go and appeal to a calculator here. Point 0.19 plus 0.132. Oh, wait, sorry, wrong, correct. Minus 0.19 plus 0.132, and then make that positive. So that that's going to be plus 0.058. And then this gives us a giant number result of 1.249. So that's if you want the total distance. But since it's from the equilibrium position, this suffices. This suffices. So the easy method works here. But if they were nasty, then unfortunately you do have to take it for a total distance, then you have to take account of it from there. And this playing around with inequalities and adding it together is called something called the triangle inequality. And this may pop up again, unfortunately, when you have to do integration. But since AI doesn't really handle too much theory, we'll just leave that when we deal with the problems. Okay, I'm done. I hope this explains everything. Thank you.